At the turn of the 19th century, electricity was all the rage. People were busy making batteries and connecting them to just about anything to see the reaction. Electricity was like a new kind of fire. One of the great battery junkies of the day was Humphrey Davy, a self-taught English chemist. In 1807, Davy was performing a battery experiment in his lab. He melted some potash, a mineral found in the ground that also forms in the ashes of wood. Chemists had speculated that potash was a compound of several elements, but had not been able to prove it. Davy wanted to see if electricity might provide the answer. He ran some wires from one of his biggest batteries to the melted potash. Pure potassium began to emerge. Davy had discovered the power of electricity to react with chemicals and transform them. Eventually, electrochemistry led to the rise of the aluminum industry, the production of semiconductors, solar panels, LED displays, even rechargeable lithium batteries. In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observed shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life. Our next great discovery is the story of Joseph Thomson and the electron.
Here we are.
So everything that we can see is made of chemicals.
That's right.
What's the future?
And they're all bonded through electron interactions.
Thank goodness.
The future.
To find out about it, I paid a visit to Harvard University. Dudley Hirschbach is a professor here and winner of the 1986 Nobel Prize in Chemistry for his research into the dynamics of chemical elementary processes. So, Thomson didn't discover the electron.
Well, it's of course said that way, but he didn't discover in the sense that he said, Eureka, I've got this thing, here it is. he did an experiment that allowed him to measure the ratio of the charge, the electric charge, to the mass. And then later he was able to get a rough measurement of the charge and therefore show that the mass was very, very small. It was about 1/2000th of the mass of the lightest known atom, hydrogen atom. So it showed that he could extract in the experiment a very small piece of an atom. Well, that was a tremendous shock. People didn't imagine. Yes, yes. Electrical piece of an atom. It was a very small part of the atom.
At the time of his discovery, Thomson was a professor at England's University of Cambridge. He was using a device called a Crookes tube in his experiments.
I happen to have here a little apparatus that's akin to the one that J.J. Thomson used in 1897. It's called a cathode ray tube, just an evacuated little glass cylinder with some electrodes. And we can hook this up and show the key points of his experiment.
A replica of the first CRT.
Yeah. It's the first cathode ray tube. It's the ancestor of the television tube, as a matter of fact. You do the last one, and we should get a stream of cathode rays or electrons going there, and it'll show up, a few of them bang into this phosphor-coated piece of cardboard there. Here, I'll give you a magnetic field you can use to deflect the electrons.
When Thomson exposed the stream of cathode rays to a magnet, the stream would bend. Since magnets can only affect matter, this meant the stream of rays was composed of some kind of electrically charged substance called radiant matter. After many hours of observing and measuring, Thomson realized he'd found the first subatomic particles. The ray was a stream of electrons. It was a revolutionary discovery.
Some years later, a student of Thomson, Ernest Rutherford, was able to show that the positive charge in atoms, which of course had to be there to balance the negative charges of these little electrons that were scooting around, was localized in a tiny, tiny nucleus, 100,000 times smaller than the size of the atom. And so almost all the mass was, of course, in that nucleus as well, because electrons are so light.
And that's still the model we have today, right?
That's the basic model for atoms, and of course the key to understanding everything involving atoms.
Like chemistry.
Like chemistry in particular, that's right.